Now we want to prove parts 2 and part 3 of this theorem, but I actually want to prove part 3 first. So I'm going to assume that we already have part 2 and then prove part 3. And the reason for that is that I think part 2 will probably take up an entire lecture at least to prove. So I don't want to start that in the middle of a lecture. And it's also nice to get the easier stuff out of the way early on, and then leave the hard stuff to the end, I think. Okay, so we're going to assume that we have part 2, and then we're going to prove it later. And we're going to prove part 3. Let's pay attention to what it is we're assuming here. A mu is a sigma algebra. A collection of mu measurable sets is a sigma algebra. That's the big one. And that this is countably additive. If you take mu star on a mu, then that's countably additive. So this is the big part of our theorem. So in other words, part 2 is saying that the outer measure, mu star, the outer measure works as a countably additive extension of mu. Part 3 is uniqueness. It's saying if you thought you had some possibly different countably additive extension of mu, then in fact it was just the outer measure all along. So what we're going to do is prove part 3, meaning we're proving that, so we haven't proven yet that the outer measure works. That's what we'll prove later, part 2. But what we're going to prove is that if something works as a countably additive extension of mu, then it must be the outer measure. The outer measure is the only candidate of something that can work. Do you want to extend, countably additively extend your countably additive function mu? If so, then you must use the outer measure. You have no other choice. All right, let's get started proving this. So actually, before I start, I want to collect some observations from part 2, which we're assuming we already have when we're proving part 3. So from 2, the mu measurables contains the original algebra of sets. And from 1, oh, no, sorry, that's from 1. From 2, this is a sigma algebra. Okay, this is going to take a lot of work to prove. So, since it's a sigma algebra containing A, it contains the supposedly smallest sigma algebra that contains A, namely the sigma algebra generated by A. So, since in part 2 we proved that mu star is countably additive on A mu, and since A mu contains the sigma algebra generated by A as a subset, it follows that mu star is countably additive on the sigma algebra generated by A. So thus, mu star restricted to there is countably additive. Okay, so I just had to get that out of the way. That's not part of a uniqueness statement. It's sort of still part of an existence statement. After all, the thing we're trying to prove here is this is the unique non-negative countably additive extension. So I should prove that it is at least a non-negative countably additive extension. Okay, so it is one, thanks to part 2 pretty quickly. Now for the uniqueness. So let's suppose that we have some other one of these, nu, and then we'll try to prove that mu star and nu are the same. So let's call it nu be a non-negative countably additive function on, I guess measure is our short word for countably additive function. And let's assume that it is an extension of mu. So nu restricted to A equals mu. Then our goal is to prove that nu was actually just mu star all along. And by mu star I mean the part of mu star that operates on there. So to prove this, I should fix some thing in the domain and then show that these are equal on that thing. So let's fix some, let's call it B in the sigma algebra generated by the algebra of sets A. Then our goal is to prove that nu of B equals mu star of B. Nu of B equals mu star of B. So to prove this equality, I will start with an arbitrary epsilon greater than 0. So this is going to be kind of helpful for managing different estimates. So the ultimate goal is going to be to show that nu of B minus mu star of B absolute value, so the distance between these two real numbers, is less than epsilon. And our goal is to show that this is true for arbitrary epsilon, so that then this difference must be 0. So this must equal this. So that's our goal. And you'll see how having the epsilon helps nudge things along. Okay, so the first thing to notice is B is something in the sigma algebra, right? Okay, that's pretty hard to work with, actually, just to have something in the sigma algebra. It's really hard to draw any conclusions about B from that, right? We've seen how hard that is. But the sigma algebra is contained in this larger and actually kind of manageable collection. So let's go back and just remember the definition. Being mu measurable means that for any positive epsilon, we can, by a modification of outer measure no more than epsilon, get down to a set that was from our original algebra of sets. So there is some set A in our original algebra of sets such that the outer measure of B delta A is less than, and then I can put any positive number I want. And I'm going to try to arrange things so that I end up with a less than epsilon here. So I'm just looking ahead at the later steps, and I think epsilon over 2 is what I want here. Now, how in the world can I get our function nu into the picture? How can I compare nu and mu star? Well, all I know about, the only thing that keeps nu behaving in a certain way is the fact that nu on A, on the original algebra of sets, is just mu. That's the only thing keeping nu under control. So my goal now is to bring things down to the level of sets in the original algebra of sets. So this is a good start, A here, but working with B symmetric difference A is not so good. A is in the original algebra of sets, but B symmetric difference A, well, that's just something in the bigger sigma algebra, not necessarily in the smaller algebra of sets. So to reduce things down further, I need to use the definition of outer measure. Okay, so the definition of outer measure, it's the infimum of all the approximations from above of this thing. If that's less than this number, so if the greatest lower bound, if this number, epsilon over 2, is greater than the greatest lower bound for the approximations from above for this number, for this set, then this cannot be a lower bound for the approximations from above. So there must be some approximation from above that's strictly less than epsilon over 2. Okay, so there is some. Okay, what's an approximation from above? Well, it's built out of, let me call it Cn, sequence in A, the original algebra of sets, that covers this set that we're trying to approximate from above, and such that the series converges of mu Cn's, converges, and let me say it in the same sentence, converges and converges to something less than epsilon over 2. So there's an approximation from above that is less than epsilon over 2. Okay, so that's good. That's our setup. And remember, our goal was to prove this, that this nu b is no more than epsilon away from mu star b. So let's start working on that. And I'm going to start with triangle inequality, since I'm going to relate each of these to nu of A, also known as mu star of A, since nu and mu agree on anything in the algebra of sets. So triangle inequality where the middle man here is nu of A. All right, so the reason I'm using this as a middleman is that this is where I know I have a nu and mu agreeing somehow. So here, due to the fact that nu and mu agree on the algebra of sets A, and A is in the algebra of sets A, I can write this as mu, right? So that's due to that fact. I can write this as mu. Can I write it as mu star? That would sure be nice. Then I'd have a difference between mu stars. Can I write it as a mu star? Yes, I can. That's because mu star is an extension of mu. So that's by part 1. Okay, so this is the triangle inequality, but I've written nu of A as a mu star of A. Now, thanks to, let's see, back here, thanks to our two results from Lemma 155, the one from this lecture actually, this one and this one, when we look at, when we have a additive function on an algebra of sets, and we look at a difference of measures, let me call them measures, even though this might not be a measure, when you look at a difference of measures, then that's bounded above by measure of symmetric difference. And then similarly here, we get the same inequality, but just for outer measure in any old situation. So now we're going to use these two. Actually, I think we can use this one both times, since we're now in part 3, where we're now proving part 3, right? And we're assuming we already have part 2. So that means we're assuming that we already know that mu star is countably additive. So by the time we have part 2, mu and mu star both fall into this category of good things here. Yeah, so let me just write down what we have and then think about justifying it. So this would be, this one is bounded above by nu of B delta A. And then that inequality is justified by this. And the other inequality you can justify by using this or that. Let me go ahead and say it's by this again. We will use this one later on. So mu star also is an additive function. So we get this. Okay, so remember our goal is to get this thing to be less than epsilon, and we are now seeing that it's a matter of controlling these two things. And we've already got one of them down, I think. Mu star of B delta A is less than epsilon over 2. So we've got that. And so our goal is just to show that this term is also less than epsilon over 2. So new goal, and if we reach this goal then we'll be finished, nu of b delta a less than epsilon over 2. Well, one thing we do have, so this is where this covering is going to be helpful. One thing we do have is that b delta a is covered by the CNs, right? So b delta a is a subset of the union of the CNs. So by monotonicity of any additive function, which nu is a countably additive function, by the monotonicity we have this inequality. So here we acknowledge this one again, I guess. And then let's see, we don't know that the CNs are disjoint, so countable additivity is not going to help, but countable subadditivity helps, which we have. Countable additivity implies subadditivity. That was, where is it? Oh, it's this one again. So we've done this again. So let's give it another check mark. And now, just as planned, we've actually reduced things down to nu being applied to things in the algebra of sets, which is where we know how nu behaves. It's mu. And, need some room here. I think, yeah, it's up here. So the whole point of this being an approximation from above was that it is an approximation in the sense that it's closer than epsilon over 2. So I think we reached the goal. And that proves, well, that proves one statement in part 3. So yeah, so therefore nu was mu star, at least the part of it on sigma a, after all. So that proves part of what we're going for. That proves this first sentence. And the next sentence is the same, but instead of sigma a, it's the mu measurable sets, a mu. So this is the unique non-negative countably additive extension of mu to a mu. So all we need to do to prove this one is pretty much modify our proof here to work for this bigger set a mu. So let's look at whether or not it's easy to just do a modification. So let nu be defined on a mu such that it's an extension of mu and it's a measure, it's countably additive. Then our goal becomes to prove that nu agrees with mu star on all of a mu. So the b I consider here should be something in a mu. Okay, and then that's my goal, and that's my goal, and now I don't need to point out that b is in the sigma algebra, therefore it's in a mu. It's directly known to be in a mu here. And so therefore I can approximate b by something from the algebra of sets, like that. No problem there, no problem there, no problem there. And I think the rest of this just works. And just therefore a mu. So a mu is where it's at, actually. That's what's going to end us up with a complete measure space in the end. So we have proven part 3. Okay, so far we've proven part 1, and we've proven that if we have part 2, then we have part 3. So it remains to prove part 2. This will be, I mean, it's fun. It's not like a torture or anything, but it takes a lot of work. So I'll put that into the next lecture.